okay, equals to okay. So we look at here, right? If the limit goes, if the limit of as n goes to infinity is equal to 0, that means that this series term will goes to, so this partial sum will goes to the square of the length of f. Okay, so this is if a non-new condition. And this one, all right, so this is called possible identity. Okay, so this is called Parsivals identity. Any questions? So this is an if and only condition. That right. So now we have a definition. And orthogonal, let's say, okay, of functions in L2 space. Okay. With respect to a weighting function of x is said to be complete. Right? Is said to be complete in L2 space if for every function, for every f in L2 space, okay, the generalized Fourier series, okay, summation Cn phi n generated by f converge to f in square adder. Okay, with respect to the weighting function of x. Okay. Any questions about this definition? Okay. So when we have an orthogonal set of functions in the L2 space, and this orthogonal set is said to be complete, okay, in L2 space if every members, or here means that every square integrable function f over the finite cost interval AB, the generalized Fourier series converge to f, right? Always converge to f. And the rest of this section is to show that all the eigensystems we discussed in section phi is complete in L2 space. Okay, so that is, so the rest of the section, the goal is very simple. Just one, to show, all right? Show that every, so an eigensystem of a regular, periodic, or singular stem-variable problems on the Frank-Cost interval, okay, is complete. And as we know that in here, the generalized Fourier series converge to F in square adder if and only if that the possible identity holds for every square integrable function F. Okay? Now we state so now we state a theorem which is fundamental for a complete orthogonal set. Okay, now I'll state it. (11.6.2). Right, so if an orthogonal set in L2 space, right, is complete in L2 space with respect to a weighting function of x, then any functions f in the L2 space which is orthogonal to every phi n with respect to the weighting function R of x, i.e. any function is 0. Right? So if we have a function in L2 which is orthogonal to every phi n in this orthogonal set, right? Must be 0. All right, must be 0 for almost all x in AB, which means that f must be equivalent to the 0 function. Okay? Now if in addition f is continuous, okay, on AB, then f is equal to 0 on AB. Not equivalent to, but just identically to 0 on AB when f is continuous. So any questions about the statement of the theorem? Okay, so if no, then I will say that. Okay, so that if f phi n is 0, so if f is orthogonal to, then, so if this is the case, right? This is the case. Then Cn, as we know, is must be 0 for all. Okay? Right. Now, since the orthogonal set is complete, since is complete in L2 AB. Okay? So we know that the possible identity holds, i.e., the square of the length of f is equal to the summation of Cn square and the phi n, and the square of the length of phi n. Okay, so that is the possible identity. Okay, and because the coefficient is 0, so this is 0. And when this is 0, the first property of a semi-known tells us that this is f is equivalent to 0. Okay, so we get the first statement. All right. So if this is true, if f is orthogonal to every phi n, then phi n, this function f is 0 for almost all x in the finite cost interval. Okay, so we have this one. Now we prove the second assertion. Okay. Now further assume f is continuous, okay, on AB. Okay, so we know f is equivalent to 0 function. Okay, now we further assume f is continuous on AB. Okay, now we suppose f of x0 not equal to 0 for some x0 in the cross interval. Suppose, because our goal is to show that if f is continuous and if f is equivalent to 0 function, then f must be the zero function identically, right? This is our assertion here. So we will prove this by contradiction. So now we suppose that f of x0 is non-zero, okay, for some point in this finite cost interval. And we will get to some contradiction, okay? So if we have a contradiction, that means that this is impossible, and which shows that f must be identical to 0, okay? All right, so how do we get to, all right, a contradiction? Okay, so from here, that then there exists, all right, a delta greater than 0 such that f of x minus f of x0, the f value would be less than f of x0 divided by 2, okay, for all x. So for x such that or for x in what? In the interval x0 minus delta, x0 plus delta. I use cost interval, okay, intersect AB. Okay. So it's a property. Suppose A here, B here, X. So if we have X0 here, such is non-zero. Okay, suppose that. Then, by continuity, that because for example, then, as we know, if we select, say here, so epsilon, so we select, okay, so the epsilon. This is, we say this is epsilon, we select, okay, epsilon. So here, so the epsilon, and then we have okay, an interval, okay, a small neighborhood, okay, and so around x0, so that for all x in this interval and the AB, because x0 may be very close to the endpoints, so we take the intersection. Okay. Anyway, all right. So that this must be true by continuity, right? So by the continuity of f at x equal to x0, okay? So that is the definition of continuity. You learned in calculus, right? So you have this inequality. Okay. And now we let CD to be this intersection. Okay. So we call this one okay. So this is called CD. And this is sorry. So whose length, okay, is positive. Okay, whose length is positive because x0 is a point in this cross interval. So, but we have left, right, and left parts. so the intersection, this finite cost interval must be must have a non-positive length. Now, things. So now, now we look at f of x, the magnitude of f of x for all x in this finite cost interval CD. Now, so we have, so this is f of x0. Plus f of x minus f of x0. Okay, so that f of x can be written as the sum of these two complex numbers. And by triangular inequality, we know that this is minus, so this one, the f value of this complex number minus the f value of this complex number, and take the f value. Okay, so that is from the triangular inequality of complex numbers. Okay? Any questions about this inequality? So for any complex numbers, A, B, right? Now, then A plus B, we know that by, okay, so we have this triangular inequality, right? You know that. And from this one, you can prove another equality, the difference. Okay. So this one can prove from this original triangular inequality. Okay, this is from, you know, that you know the length. So this is in vector. Suppose this is vector, right? Because complex number can be, think about a two-dimensional vector. Do you know that in high school? In the complex plane, right? Every complex number can be regarded as a two-dimensional real vectors. Okay, so you can see this is the H B. Okay. Right. Okay. So the length of this edge is less than equal to the length of the sum of these two lengths, these two side, right? And the length of this side is greater than equal to the difference of the length of these two sides. That is the from plane geometry. But actually, it's related to such kind of triangular inequalities. Okay. All right. So we just use the triangular inequalities. So 1, 2. So they are all called triangular inequalities. All right. And so this is there's a difference. Okay. Now, but as we know, this quantity is less than half of this quantity, so that this difference is has a lower bound divided by 2. Okay. Right? And this is greater than 0 for all x in CD. Okay? Right. So by continuity, so when f is non-zero at a point, all right, at the point x0 in this finite cost interval, then we will find a non-zero, okay, a finite cost interval CD with positive length, such that f of x is non-zero, all right, on the whole subinterval. Just like here, right? We can find that if f is non-zero at x0, then we find a small interval, right, around x0, such that the function is non-zero. Okay, so this is the way we show here. All right, and so now the length. Okay, the length is this integral. All right, and this is greater than or equal to CD, because CD is a subinterval of AB. So that so this is the x. But we have lower bound, so we have okay, and this is positive. Okay, because the weighting function is positive. All right, on the open interval AB. All right, except possibly at the endpoint. But so in this, because this interval has positive length, so that this integral is always positive. All right, so we have that f has zero positive length. Okay, so this implies that f is not equal to 0, not equivalent to 0. So this is a contradiction. Okay, so right now we get a contradiction here. We get a contradiction. All right, so we conclude that f is identical to 0, okay, on AB. Any questions? This one? Because we just show that the magnitude of f of x has a low bound, right? This is the low bound of this, the function value, the magnitude of the function value for all x in this finite cost interval CD. And so when we in here, we just restrict ourselves to this subinterval of AB, because CD is a subinterval of AB. Okay, and for all x in between C and D, we show the magnitude of x has a low bound, so we apply low bound here. No, we don't have. Oh yeah, yeah. I have to put square. I'm sorry. Yeah, thank you. Yeah, yeah. That's your question. Good. It's my mistake. That's great. So That would be, thank you. Yep. Okay. Other questions? Yeah, so my notes, yeah, so please correct the error. Yes, thank you. All right. So, so that this is a fundamental property, all right, for a complete orthogonal set. Right, complete orthogonal set. So a consequence, we can see that. So a consequence of the theorem is that if we remove, okay, so if we remove a member from a complete orthogonal set, then the remaining set all right, so then the remaining set is not complete at all anymore. Okay, so if this orthogonal set is complete, if you remove any one phi n from this set, right? If you remove just any one only, right? Then the remaining set, even though again it's an orthogonal set, but will not be complete anymore. Why? 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 Okay. So you have to think about that. Why this is true? Okay. If we pick up, for example, phi 1, okay? We take one out phi 1. Okay, so the remaining orthogonal sets from phi 2, phi 3, etc., right? Now, if phi 2, phi 3, etc., form an orthogonal set, which is complete, right? If the remaining set is complete, what happens? We know phi 1 is orthogonal to every other phi n, right? So by the theorem, then phi 1 should be equivalent to 0. All right? And so phi 1 has 0 length, right? But we say that we consider orthogonal set which has non-zero length already. So that is a contradiction. All right, so it's impossible. Okay. Okay. Okay, so the reason is that we assume that any member in an orthogonal set is not equivalent the zero function. Okay, maybe I will say we considered so please prove it at home. Okay, so prove. Okay, and so now our job for the rest of this section is to show that any eigensystem of regular, periodic, or singular stem-Liouville problem is complete in L2 space. Okay. All right. So to answer, okay. So so we need the following approximation theorem. Okay. So we need the following approximation theorem. (11.6.D). So we can approximation for any square integrable function f on AB, there exists a sequence Fn of infinitely differentiable. Okay, complex or real valued functions on AB. Each, okay, being 0 in both a neighborhood of endpoints A and a neighborhood so endpoints A and a neighborhood of endpoint B which, okay, converges to F, okay, so which converges to F in square error with respect to a weighting function of x, i.e. the limit of n goes to infinity f minus fn square equal to 0. Okay. And I have give a reference of such an approximation theorem. So it's a theorem, right? Of course, its proof is non-trivial, so I will not give a proof for you. It just shows that for any square integrable functions, you can always find a sequence of very nice functions, so infinitely differentiable. So each f of n has derivative of arbitrary order, okay, on AB. And each fn will be 0 in, so at the point. So I will show you that this is A, this is B, right? So now suppose we have this one. All right, suppose we have, so this is f of x. So f of x, can see it's piecewise continuous, of course. This is just an example, right? So it's square integrable, right, on AB. And then we can find a sequence of infinitely differentiable functions. Okay, so the first one would be 0. Okay, and so maybe here. All right, so we see that it's 0. You can see. So this is f1 of x. Okay, so f1 x is infinitely differentiable, right, at every point, and it's 0 in a neighborhood of endpoint A and a neighborhood of endpoint B. Now the second one could be like this one, also 0. And beta, right? Beta. Okay, so this is f2 of x. Again, it is very smooth because it's infinite differentiable, but it's also a 0. Okay, at a neighborhood of endpoint A and a neighborhood of endpoint B, etc. So this is also, again, maybe it's better, become sharper and sharper. Okay, so this is f, etc. So you can always find a sequence of infinite differential function. Okay, and also in both a neighborhood of A and neighborhood of B, that the function has 0 value. Okay. So this is the very good approximation theorem. Okay, and I have given a reference for you. Okay, in my lecture notes for proof. So any questions about this approximation theorem? And this is good for with respect to any weighting function. Okay, so you can always construct. Okay, so even though you you have the original function f of x and may piecewise continuous or maybe very irregular, but you can always find a sequence of infinite differentiable function. Okay, to converge to it in square adder. Okay. Any questions about the theorem? Okay, so we will use so now we are able to prove that the trigonometric system we discussed at the beginning sections is complete in L2. So it's about completeness. Right. So the trigonometric system. 1 cosine x, sin x, cosine 2x, sine 2x, etc. Okay, is complete in L2 minus pi to pi. Okay, so now here is the proof here. All right, so so let F is in the L2 space. Okay, right, and Sm the partial sum functions, okay, of the trigonometric Fourier series generated by F. Okay. Right, and now we fix. So we fix an epsilon greater than 0. So we fix a very small number. So by the approximation theorem, okay. So by the approximation theorem, there exists a continuously differentiable function G on pi with g minus pi equal to g pi equal to 0, such that f minus g are less than 2. Okay, so I forgot to put and the r is 1, so I just, because we are considering, so the weighting function is 1. Okay, the weighting function is 1. Okay, so let me okay, so it's 1. So when it's 1, we just remove the index here. Okay. All right. So and the g is here because that the square of the distance between Fn and Fn goes to 0, right? For any weighting function. Now we can select Fn. So we just let G to be some F sub n, which little n is big enough, such that this length is less than the required upper bound. Okay, so that we can always find such a function, and such a function is infinitely differentiable. So at least it is continuous differentiable, because it is differentiable over any any order. So it's continuous differentiable, and we know that at the two endpoint they must be 0 because that every f sub n is 0 in a neighborhood of endpoint A and a neighborhood of endpoint B, right? So at least that this we have this value here. Okay. Do I have any questions up now? Okay. And so now we let summation, we let alpha 0 plus alpha n cosine nx plus beta n sin nx be the trigonometric Fourier series, all right, generated by G. Okay, so for this G, it has a trigonometric Fourier series. Okay, right? So of course, because G must be absolutely integrable, right, over this interval, because it is continuous, of course. Now, and this, which, all right, so this which converges, all right, to G uniformly, okay, on minus pi to pi. Okay, by theorem 11.4.8. Okay. So in section 4, we have developed several theorems about uniform convergence, and because G is continuous, okay, G is continuous on the whole finite cost interval, so that and it is continuous differentiable, so its derivative is also continuous, and so in that section we show that the trigonometric Fourier series not only converge to G, but also converge to G uniformly. Okay, so we have uniform convergence, right? And this has been stated in theory 11.4.8. But uniform convergence implies convergence in square error, right? As we show by theorem 11.6.8, uniform convergence implies convergence in square error. So that so by theorem, this sequence, this series alpha n okay, so the series converge to G in mean square error, in square error. Okay, so that there is a positive capital N at G minus Tm less than 11 divided by epsilon divided by 2 for all m greater than or equal to n, where Tm of x equal to the partial sum, so it's alpha 0. Okay. Okay. So this is the situation. Is that okay? So uniform convergence implies convergence in square error. So the partial sum function of this trigonometric Fourier series generated by G, okay, has this property. Okay. So now we have f minus Tm. Okay. So now f minus Tm. Okay. So what is Tm? Tm is a partial sum function of this trigonometric Fourier series generated by G. Okay. And so this is equal to f minus G plus G minus T sub m. All right. And by triangular inequality, so this is equal to f minus G. This then f minus the length of between f and G, and the length between G and Tm. But the distance, the distance between G and T and G is upper bounded by half of epsilon, and the distance between G and the partial sum function T sub m is also upper bounded by half of epsilon. So that they are here. Okay, here. So for all m greater than or equal to n, okay. So f minus Tm. Okay. Now again, by theorem 11.6.b, we know that f minus xm. So what is Sm? Sm is the partial sum function of the trigonometric Fourier series generated by f. Okay, so this is a partial sum function. So this function has the minimum adder. So we know we have this inequality. Okay? They use the same trigonometric system, right? So they use. Okay, so we have this upper bound. This is from theorem 11.6.b. Okay, and so this is an epsilon for all. Okay. All right. So for any given epsilon, we can find a little capital N such that we have this inequality. So this implies that limit for m goes to infinity equal to 0. Okay? So that the trigonometric system is complete. Okay. Okay. So the approximation theorem, the role of this approximation theorem is to provide us good approximation to any square interval global function by a nice function. Okay, so here the nice function g, which is continuous differentiable function. Okay, and we know that such a nice function can be represented by trigonometric Fourier series. And the trigonometric Fourier series generated by this nice function will converge to G uniformly at every point. Okay, and which implies that this trigonometric Fourier series converges to G in square adder. Okay, in square adder. So for well-behaved function, all right, such as continuous differentiable function on AB, uniform convergence of course implies convergence in square adder. So square adder is a weaker condition, right? But we can use such a G as a middle step to go for a strong result that to show for every square integrable function f, f can be represented by its trigonometric Fourier series, okay, in square adder. Okay, so this is it's quite a standard approach to do the proof. Okay. Any questions? And right? And the rest of this section in the lecture notes develop the following results. First of all, an eigensystem of a regular or periodic Sturm-Liouville problem on AB is complete in L2 space with respect to the weighting function x. Okay. Second, the eigensystem Pn of the Legendre Sturm-Liouville problem on mass 1 to 1 is complete in L2 mass 1 to 1. Okay, so Pn is the Legendre polynomial. Okay, I discussed in section number 5. Okay. Unfortunately, I didn't have enough time to cover it in the lecture in the classroom, but I have asked you to self-study them. Okay. And also shows that the eigensystem, okay, J nu alpha nu n x divided by b. So this is the basal function of the first kind of order nu of the basal Sturm-Liouville problem, okay, of order nu greater than or equal to 0 on 0 to b, right, is complete. It's complete in L2 0 to b with respect to the weighting function r of x equal to x. For Legendre function is also, yeah, so the weighting function I think is 1. Okay. Right, so please self-study the rest of lecture note, section 11.6. Okay. Right. And so I have to move on to the next section. Okay, so we have studied representation of functions defined on finite cost interval. Okay. All right. Now, how about to represent a function defined on the whole real line, or just half of the real line? Okay. So so in this section, we will lay some foundations. Okay. So we will lay down foundations for such a representation. All right. So so suppose f is an absolutely integrable. Okay. Absolutely integrable complex or real valued function on. Okay, so and which, for example, which is maybe I just write that. Okay, so maybe I just write here. F is a piecewise continuous. Oh, no. Yeah, sorry. I have to say an absolutely, integrable complex over real valued function on the whole real line, and which is piecewise continuous on any finite subinterval. Okay, of the real line. So in any finite subinterval of a real line, f is piecewise continuous. Okay. So it has, in each finite interval, there exists only finite many points of discontinuity. Okay, so that is the idea. Okay. All right, and has the left hand derivative and the right hand derivative at every point in the whole real line. Okay. So this is the function that we consider. All right, and then we let f and subscript by L we define here. So this function is equal to the original function when x is in between minus L and L, but will be 0, right, at the end point. So that the idea is here, probably. Okay, so this is f of x, right? So f of x is defined on the whole real line, and select minus L and L here, and so that we will, so they will be the same. All right, so we just arbitrarily define that at the endpoint, the value is 0. So that is a truncation. Okay, so we truncate the original function, all right? The original function to a function defined on a finite cost interval. Okay, so let be the truncation of f of x on the finite interval minus L to L. Okay, so we just truncate the function. All right, and then we regard, so by regarding f sub L x as in a period of a periodic function. Now the endpoint is 0, so it's easy to define a periodic function. Okay, so it's a good choice, so that this function just in a period of a periodic function with a period. To L. Okay, and so by theorem 11.1.2, f of x can be represented, right? So can be represented by Fourier series. Okay, on the finite interval, which is an open interval. Okay, because the endpoint may be arbitrary, but at least, right, in the open interval. Okay, so in the open interval, so that in this open interval, okay, the average of the left-hand limit and right-hand limit at the point x in this open interval can be represented by the trigonometric Fourier series. All right. So we have this one. Yeah, because that, as we know, f is piecewise continuously on any finite interval. So this function is piecewise continuous on minus L to L. Okay, and it has left hand and the left hand derivative and right hand derivative at every point. Okay, so that it fulfills the premises of theorem 11.1.2. So we have this representation. Okay, and the coefficient here L0, it's 1 over 2L minus L to L f of x dx. Okay, and a ln is 1 over L minus L f of x cosine m pi x d over L dx. And b ln is 1 over L minus L f of x sine m pi x dx. Okay, so we have that. All right, because in this interval, all the f sub L x can be replaced by f of x by the definition here. So we just write it down here. Okay, so you know that the coefficient depends on L, the length of the finite closed interval you choose. Okay, so that's why we put a big L here to say that it depends on the L we select. Any questions? Okay, so at least in such a a finite open interval, okay, that every x can be represented in this way. So of course we can enlarge L, right? We can enlarge L. We can enlarge L to know that we have a representation for if f is far away from 0. Okay, but when you change big L, you change the coefficients, right? So that is it's terrible, right? It seems like when you change L, you have to recompute the coefficient again, right? So it's not a good idea, right? It's not a good representation. All right, so now we will see, right? Now, so now we will insert all this formula into this equation. Okay, so now, okay, what we have. Okay, and so this one is this integral to L. So we do the substitution, and 1 over L, and the summation k from 1 to infinity, and the integral fu cosine k pi u divided by L and the du. Okay, so this is a sub ln, and the cosine n pi x l plus integral from minus L to L f of u, and the sine k pi u divided by L du, and the sine k pi x divided by L. Okay, here. So we just do the substitution of all the coefficients into this expression. Now we will, because eventually we will get rid of the parameter L, okay? And we will let L goes to infinity, right? Goes to infinity. So for this purpose, now we will define, change of value, define delta omega to be pi divided by L, okay? Pi divided by L. So in here, what we change is to pi, okay, and L minus L, fu, and du, and here we have pi divided by L, right? So this will be delta W, okay. So we will divide by pi, but multiply pi here, and similarly. We will express the series sum to be limit of partial sum. Okay, so n goes to infinity, and 1 over pi here, summation k from 1 to n. Okay, and here minus L, and the fu, okay, and the cosine k pi divided by L, and the u here, okay. So here and the du, okay. Because we will do this kind of substitution. So now, and we have cosine. Oh, I forgot. This is k. I'm sorry. Okay, so cosine k pi divided by L x, right? Plus this one, L minus L, fu, sine k pi L u du. Okay, and here sine k pi L x together, and finally we have L. And the scaling is because that we change 1 over L by 1 over pi, so we have this scaling factor. Okay, so we have this scaling factor here. Okay, so this is the delta W, and delta W, delta W, delta W, delta W, and the delta W here. Okay, and so that so this one becomes to limit and goes to infinity, and goes to infinity, and 1 over pi. So we can move 1 over pi out, and the integral and the f of u here. All right, and they have a lot of du, so that we have 1/2. So this is 1/2 here, plus summation k from 1 to n. Okay, here, and fu has been factored out. So we have cosine and the cosine, sine and the sine, right? So now we have cosine k delta w u. Okay, here, and the cosine k delta omega and the x here. So this term plus sine k delta omega u times sine k delta omega x together. And now multiply with the du. Okay, so the integral, we merge 3 integral together. Okay, together. So we have the integral here, and the constant delta w here. All right, and we have that. And so you can see we have the sum angle identity, right? So cosine, cosine, sine, sine, right? And so this becomes to limit 1 over pi f of u 1/2 plus summation k from 1 to n cosine k delta w u minus x. Okay, and the delta w and du. So okay, so we have for all okay, so the representation becomes to such a simple formula here. Okay, now we can simplify this sum, right? So we will use a formula that the summation cosine k theta. So if we have theta here, if we multiply this is series sum by half of sine of half theta, then we can have half of sine k plus 1 half theta minus sine k minus half theta. Okay, so they can cancel each other, and so finally we have a sine n plus half theta minus sine half theta divided by 2. Okay, And when we divide the sine half theta on both sides, okay, so divide both sides. We have so now and move 1/2 to here, so that 1 plus summation k 1 cosine k theta becomes to this ratio sine n plus half theta and 2 times sine half theta. Okay, so we have this one. So now by letting theta to be delta omega u minus x. Okay, so we can think about this is delta. This is theta. All right, and so the integral can be so we have x minus fx plus divided by 2, okay, is equal to limit n goes to infinity 1 over pi, and f of u, and here is sine n plus half delta w u minus x, and 2 sine 1/2 delta w u minus x, and delta w du. Okay, so now we can do some simplification by letting. So we let v to be u minus x, right? So when we let u minus x, we change the variable L minus x minus L minus x, and f of u plus x, v plus x, and sine n plus 1/2 delta w v 2 sine half delta w v, and the delta w dv, and where v is defined to be u minus xx. Okay, by letting here. Okay, so right. So next week I will start from this formula. Okay, in here we know n will goes to infinity. Okay, n will goes to infinity. And here, right? N is here, and so we will try to eliminate the effect about the L parameter, because with L parameter that it will be cumbersome, right? Even though we have this representation, but the coefficient will depends on L. Okay, and so we will try to find a nice formula for representation, okay, for all x in the whole real line. Okay, all right. So this result has been deduced from what we have before. Okay, what we have before. Okay, and so this is a good starting point to have. All right, and about the midterm examination, I will postpone the midterm examination by 1 week. So that would be November 4th. Okay, instead of next Thursday. Okay, so and the coverage I think will be the whole chapter 11. Okay, yeah. All right, so I stop here.